Okay, today we talk about precipitation processes. My name is Hua Guan from School of the Environment, Flinders University. Now we're going to discuss the atmospheric processes that lead to various types of precipitation. And this content will be useful to understand precipitation spatial distribution, precipitation seasonality, extreme precipitation events, climate variability and change, air pollution, and precipitation formation. Now, the first two issues are familiar to you, right? Now, the third one, extreme precipitation event like tropical cyclones, you may have heard about that. Now, the last two probably you are not very familiar. Recently, Goethe Institute released a research report, and they say the report says with global warming, precipitation in Adelaide and the Mount Lofty area will reduce. How do we understand that, right? So what we discussed today may help to understand that report. And also recently, people are concerned about air pollution effect on precipitation. And some people argue that the air pollution has reduced precipitation. So the mechanism, we're going to touch some of that in this mini lecture. To understand this lecture better, you need to have knowledge about saturation vapor pressure, latent heat of vaporization, and then generally vapor distribution in the atmosphere. You haven't heard about these terms and knowledge, and you can check out this YouTube mini lecture, and I have this website post here. Now first, let's look at the vapor saturation vapor pressure versus temperature curve on the main panel. This tells you the capacity of the air to hold water vapor is a function of temperature. Now look at that black dot represent the point along that saturation vapor pressure curve. It tells an air parcel at 30 degrees, it can hold vapor with the vapor pressure to about 30 millibar. That is the capacity. It doesn't mean air at 30 degrees always have that vapor pressure, right? So for example, the red dot is actual air at 30 degrees, but only have vapor pressure about 15 millibar. So at this condition, the air, there's no condensation because the air can hold more water vapor. Now, if there's some mechanism or process lead to the temperature reduction to about 13 degrees, now this air parcel has vapor pressure is lying along this saturation vapor pressure line. So this means it cannot hold more vapor, right? So condensation may happen here. So this temperature, we call it dew point temperature for this air, right? Okay, now we know that the temperature decrease of air may cause the condensation to happen. And now I show you one example. This is a dew collector experiment, a dew collection experiment that we have done a few years ago. The experiment was done by a group of students. So first, I think on this graph, I show you the horizontal axis is the time, right, from one day, afternoon, or early evening, 18 o'clock, through the night to the early morning in the second day, 8 o'clock, 8 a.m. And vertical axis is temperature. And here you have a 5 curve. The black curve in the middle is the dew point temperature. Okay, then the 2 curve above that dew point temperature curve is air temperature. One at 0.4 meter, the other one at 2 meter. So you can see air temperature is higher than dew temperature. It means air can hold more vapor, right? Can hold more vapor, and so there's no condensation happen. So you won't see any fog in the air. And the other 2 curve below the dew point temperature curve is the temperature on the dew surface, a dew collector surface. And you can see temperature of this dew collector surface actually is lower than the dew point. It means condensation may happen, right? So the interesting thing that we see this one interesting pattern in that temperature with time curve is the temperature suddenly increase at around 2 a.m. and then keep at high level to about 2 hours. Yeah. What happened here? You understand this phenomena, that will help us to help you to understand the precipitation processes. Yeah, think about this and bring your answer to the class for more discussion. Now, previous slide showed condensation happen on the surface, right? And now you can see condensation happen in the air, in the atmosphere. That's what you see. The cloud. Cloud is not vapor anymore. It's the condensation of vapor into liquid drop or ice, right? To understand that condensation in the atmosphere, let's start with the first law of the thermodynamics. This law says the change of the internal energy of a closed system is equal to the amount of heat supplied to the system minus the amount of amount of work done by the system on its surrounding. The equation is delta U. U is internal energy. Delta means change of internal energy equal to Q minus W. Now here I like to explain what a closed system is. A closed system means a system does not exchange material with its surroundings, but there's an energy exchange, but no material exchange. Okay. For example, let's look at a pot. You boil, well, not boil. You warm water. Right? You warm water in a pot with the pot is covered by covered. Right? It's sealed. Then when you heat it, and that pot, the system is a closed system. There's no material exchange, right? Because you seal the pot, and you heat it, the system, and you will see the system actually internal energy change. You can see temperature of the pot start to increase, right? So now these tell you one example of how it works. And then you also see that temperature can be an indicator of the change of internal energy. Now, what about a system without heat, a closed system without heat exchange? If there's no heat exchange, then we call this system is a adiabatic system. And so the first law can be reduced to delta U equal to W. W is work done to the surrounding. For the air, if the air expands, simultaneously it does work to the surrounding. Then it means, based on this law, it means internal energy of the air will decrease. Okay? If its internal energy decrease, it means, well, you will see from temperature will decrease. Okay? Now, this is the point I'll try to make. If the air moves from one location to another, and during this movement, if this air expands, you expect to see temperature decrease. Now here it's important to remember there's no phase change. Okay, there's no phase change. This law will tell you the temperature will decrease if air expand. Now, how, at what situation air can expand? Right? Think about this. If air move from one air pressure to another lower air pressure air environment, it may expand, right? So this happen in the atmosphere. This graph show you the air pressure change with the elevation. Okay, the graph, the horizontal axis show you the pressure. It's unit of millibar, right? It's 100 Pascal. And vertical axis is the elevation. So you can see air pressure decrease with the elevation. Now think about it. You have an air parcel move from ground surface, well, close to the ground, and move upward, right? Then it starts to expand because the surrounding pressure is lower, right? So it expands. When it expands, temperature will decrease. So this why we see the temperature decrease with elevation. Right? That's shown in this dot curve. Yeah. Now, with this knowledge, it's easy for us to understand precipitation process. Okay, this graph is produced by my colleague, Dr. John Bennett at Flinders University. Well, it reproduced from other publication. Okay, and now there's in your textbook shows there's 4 steps leading to precipitation. First one, we already talked about that, is cooling the air, right? Cooling the air need to get cooling down to dew point temperature. When it is at dew point temperature, condensation may happen. If there's a surface like on ground, like your car, you park your car outside. If the surface temperature is cooled down to dew point temperature, dew may form on your car. So you can see sometimes dew form on your car if you park your car outside. And this can also, you can see in this when you camp, right? In the morning, you can see dew form on your tent. So that is what happened, condensation, cool down the air, leading to condensation. But what about in the atmosphere? There's no surface for this air to condensation water to attach to. So what happened there is in the air, we have a condensation nucleus, right? Any solid or even liquid drop in the air like salt, right, or dust. So that can serve as a condensation nucleus. So the vapor condensation will attach to that nucleus. That condensation nucleus very small, like 0.1 micron, right? And then this condensation will attach to that and then grow into like cloud drop. Typical cloud drop is about 100 times of condensation nucleus, 10 micron radius. And then this cloud drop can keep growing into raindrop. Now, the typical raindrop has a size of 1,000 micron. It's about 1 millimeter radius. And And when you have a raindrop of that size, the gravitational force will force this raindrop to move downward and can lead to a terminal velocity. It's about 650 centimeter per second. So it's 1 second can fall about 6 meter. Right? Okay, but there's one more mechanism you need to make rainfall to happen. Because if this happen in the atmosphere, you only have one raindrop, right? So you need to have a lot of raindrop, and that is you need to have a importation, continuing importation of water vapor into the air, so that can sustain that process, then cause the rainfall or snowfall or other types of precipitation. Okay, next we move to actual weather systems leading to precipitation. And up to now, we understand that the cooling of the air is essential for precipitation. And then we know that because of the pressure vertical profile, so you move air upward, air will expand, will cause cooling. So uplift is the necessary process leading to precipitation. And there's different mechanisms leading to uplift of air. And first group of mechanism is due to convergence. So it means air near the ground, near the surface, air move together, move toward each other. And you move toward each other, and then at the convergence zone, air has to be lifted up, right? So that is one major mechanism. And also, another mechanism is related to thermal convection. If the surface is hit by solar radiation, and that may cause convection, if up to one enough scale, then can cause a large scale uplift of the air. And then the last one is topography cause uplift of the air. Okay, we'll go through each of these. First, due to convergence, that's to the large global scales one, occur in the equator. So you heard about this atmospheric circulation. There's one circulation called Hadley cell circulation. It happened in the lower latitude area. Near the surface, air moved toward the equator from both hemispheres. Okay, when so air converge around equator zone, and then this air has to be lifted up into the atmosphere, so that causes cooling. Right? So this zone, we call it intertropical convergence zone. You can even see this convergence zone from satellite. Right? You can see this cloud distribute along this within this zone. Now another convergence is due to the low pressure. Even in the near surface, you have a very low pressure at a certain point, and then surrounding air will move toward this low pressure center, and then will cause a system, we call it cyclone. And this usually happen in tropical area. And here I show you one example from satellite image. You can see this cyclone. You see this at that center of the cyclone, air has to be moved upward, right? Now, I also check out recently 2 tropical cyclone near the Australia area. That's 2, and then look at this sea surface pressure chart. You can see corresponding to, low pressure center. Right? You can don't worry about the unit for the moment. Just look at the number. The center, 1 toward left, in the northwest corner of the Australia has I think is 1004, and the surrounding is 1006, and toward outside further is 1010. Now the other one is about 1002 in the center, and then grow the pressure increase to outside. You look at further to the east, you can see another much stronger and bigger low pressure. That's another tropical cyclone there. Okay, now you know that low pressure can cause air uplift. Now, one thing I probably like you to look at this satellite image and look at the pattern. You can see almost how the air move in this tropical cyclone, right? Its surrounding air move anti-clockwise toward the center. My question is, what happened to the two tropical cyclone occur in Australia? It's also anti-clockwise toward the center of this cyclone system. Yeah, think about that and bring your answer to the class for discussion. Okay, now next two slides, I'll tell you another type of convergence. It's two air mass move toward each other, have a different property, thermal property. Now, this first one, I call it a co-frontal system, or you just call it co-front. And this system had two air mass, right? From left-hand side, it's a cold air, and right-hand side is warm air. Now, in this system, cold air is more active, is stronger, move toward this warm air, and we know that cold air and warm air, they have a different density. Warm air usually lighter, so it locate up above the interface. So cold air move to this toward this interface, force the warm air to rise. When warm air rise, air temperature cool because it expands. So air temperature reduce, cause condensation. So very likely leading to precipitation, and this precipitation usually is limit to a certain narrow band and relatively intensive. Okay, compared to another front, we call it warm front. So it's this one. In the warm front system, still there's a two air mass converge, right? But in this system, the warm air is stronger, so it climb up along this interface, leading to relatively wide precipitation band, and precipitation intensity is relatively lower than another one, cold front. Okay. Now third one, not third one, sorry, that's another situation or a conversion leading to uplift is on the land surface, different area is hit up by the solar radiation differently. So if we have area relatively hit more by the solar radiation, air become warmer, and then it move upward. When you move upward, so that is the uplift air. If we reach a certain spatial scale, can lead to thunderstorm. Okay. Okay, the last one is a orographic uplift. So you have air, moist air, move toward the mountain range, and then the mountain range force this air rise, and then cause condensation and precipitation. And this is one example. But if this air, after this air, move past this summit of the mountain range, go to the other side, and air actually descend air actually warming up. It warm up, then there's no condensation happen, right? So you will have a very low rainfall. So now you see these two slopes very different from the, in this case, from the left-hand side or wet side, and we usually call this is windward slope. Windward slope. Now the other side is, we call it leeward slope. So they have a very different precipitation distribution locally. With all this mechanism, now we can come to this global annual precipitation map. And now you should be able to explain why in some area it's very, very wet, right? In other area it's dry, like dry, like in North Africa area, or the in wet area like Amazon area, very wet. Right? You should be able to explain, interpret why these precipitation distribution like this. And then further in class, we'll talk about the Australia precipitation distribution, particularly in South Australia and in Adelaide area, what the precipitation pattern. And we also talk about the climate change impact on precipitation in our area. Now, the other one, I also like you to think about this area, right? In the high precipitation area in between China and South Asia, India, right? In that, it's very high precipitation. What happened there? Similarly, you can see in the western west coast of North America and some part of South America, some part of North America. Right? Okay, try to think about this and bring your answer to the class for discussion. Okay,